familiarize yourself with some of these in your nursing courses. So,
well, I used to be surgical tech, so woohoo!
yeah, you know that. So sterilization, that's to destroy all microbial life. Disinfection, that just reduces the number of pathogens so they are not as likely to cause disease. Now, keep in mind that you disinfect inanimate objects. So like tables would get a disinfectant, computer keyboards, things like that. Decontamination, typically I don't ask you that, but renders a contaminated surface safe to handle. Antisepsis targets microorganisms on living tissue. So sometimes I ask that comparison. An antiseptic you would use on tissue, a disinfectant you would use on an inanimate object. The term microbiocidal versus static, remember cidal means killing. And there's different groups that these can fall under, such as certain ones that target fungus, protozoa, so forth. There's some that have a little wider scope. So microbiocidal would just be killing of certain groups of organisms. And static would be to inhibit the growth. So things that are microbiostatic are more inhibitors. I really had to look for this. It's funny. I was like, is that in your pocket? It's so small. I know. It was right there. I looked on your desk and I was like, it happens. Decimal reduction time, sometimes called the d-value. All this is the time required to kill 90% of the cells. Now this obviously would fluctuate depending upon the organism. So some of the things that they subject these organisms to would be various temperatures. So heat treatments would be an example. You don't have to worry about the last two things, physiological state or other substances. But keep in mind that the temperature would vary depending upon the type of organism. Obviously, the temperature would increase, for instance, if it was a spore former versus a non-spore former. These are all straight definitions here. The thermal death point is the lowest temperature to kill all microorganisms within 10 minutes. The thermal death time is the minimal time to kill microorganisms, and this is typically done in a liquid suspension at a given temperature. So here, this can vary depending upon this. Up here, you're really trying to restrict yourself to a time limit. So that temperature obviously can be elevated in that particular scenario. It's going to be a pretty high temperature. Now, some of these things, the autoclave you've already learned, but as far as some physical controls, the first one is heat. There's two different types, moist heat and dry heat. Moist heat is most commonly used. That's probably the most popular method, such as autoclaving. But the first one is boiling. And boiling does kill most vegetative cells. It's not completely considered sterile. So for some spore formers, boiling doesn't exactly work theoretically. The autoclave is good for sterilization, so eliminating spore formers. It's steam under pressure, and if you were to open that autoclave while it was still going, it'd make a nice loud whistling sound, and the whole place would fill up with steam. So you could really tell the pressure if you ended up trying to open it. But as far as the requirements, remember it's 121 degrees Celsius for 15 minutes, and it's at 15 psi, and that's the pounds per square inch that I have here. That's 15 psi. Now, pasteurization, they've since come out with ultra pasteurization, which I don't require that you know on the exam. But pasteurization only targets certain microorganisms. So there are two different methods that are commonly used, the flash method and the batch method. The flash method is 71.6, and they usually are rounded up to 72 degrees Celsius for 15 seconds. And so it's really fast, and that's why they call it the flash method. Now the other one is 63 to 66 degrees Celsius for 30 minutes, so it gets exposed for a longer time period. Now, ultra pasteurization, I can't remember what the temperature is off the top of my head. I think it goes into the hundreds, and it does kill a lot more organisms, especially things that are like organic and some of the other items that they really have a need to eliminate the amount of organisms will be subjected to ultra pasteurization. So ultra pasteurization does kill more organisms than it is higher temperature. I think things taste better that are ultra pasteurized, but I think that's maybe a little psychological. I don't know. My husband did a taste test with me one time. And you know what? He mixed them up so much that it confused me at one point. You know, it's like the smelly stuff when you go, you got to reset. He never let me reset because I picked the right ones first time. And he's like, well, I'll try it again. Well, now it all just tastes like mush, so I don't know. I don't like milk anyway, but it's fine. Now, another way that you can sterilize is using dry heat. And a lot of times they'll use ovens for these types of sterilization procedures. But this is old numbers here. This is the numbers that I want you to know. The temperature is between 150 to 180 degrees Celsius. And one of the things that I want to point out is that you have to increase the temperature when you're using dry heat as opposed to the moist heat, because that pressure is not quite as prevalent as it is with the other procedures. But 2 to 4 hours for sterilization. So you got to increase the time, you got to increase the temperature. And obviously if it's a spore former, you might max out on time and the autoclave, you don't do anywhere. All right, as far as another physical control, cold, that's meaning refrigeration. As far as refrigeration goes, it doesn't necessarily kill the organisms, but they begin to die off slowly. So it is very useful in slowing growth. So, for instance, if you have urine cultures that you need to send off, putting them in the refrigerator, that's a nice way to kind of stop those organisms just from flourishing, because then everybody's got a UTI when you do that. When you just set it out. And there's places that have done that, so it's not a good thing. Radiation, another control there. There's non-ionizing versus ionizing radiation. The example I give you for non-ionizing is UV light, and it would sterilize by targeting that DNA or damaging it. A lot of times in our country, we use it more at a disinfectant level. So you can adjust the levels that the organisms actually get. Germicidal lamps are an example. A lot of times when you go get your nails done, they might have something like that there. Ionizing radiation, X-rays and gamma rays are examples of that type of ray that we use. As far as still targets the DNA, but it sterilizes by stripping electrons. And things that they might use this on would be food. There have been a lot of debates on how much antibiotics, especially in agriculture, we should feed various animals due to antibiotic resistance. So there are countries that actually do limit the types and amounts of antibiotics that can be given to the animals that you're eventually going to eat. So there was a time period where they did do a lot of food exposure to this type of radiation, but says it's at levels that doesn't affect our DNA. I don't know. Probably everything really affects it anyway, so not as common, but drugs, vaccines, medical instruments, surgical gloves, those are things that typically sterilize using this method. And even when you get into those surgical gloves, you can understand why that would be a preferred method. And some of those things also break down if you put them in the autoclave. But if you put gloves in there, what's going to happen? They're just going to melt, right? So there's different methods dependent upon what you're trying to sterilize that would commonly be used. Now, other controls, filtration. This one, this is more of a physical means of removing an organism. So sometimes they'll call it a mechanical method. Things that are heat sensitive, like media, vitamins that might break down if you autoclave over time. Typically, media is autoclaved anyway, but you don't want to autoclave it so many times or else it's not any good anymore. So you can filtrate to actually remove some of the microorganisms. It doesn't mean that it's a completely sterile method. Now, as far as drying goes, that's not sterile either. A lot of organisms are lyophilized and kept in that form. They're not actively growing, so they're very static in that particular procedure, but you can actually store them that way. Osmotic strength, a lot of times people will add salts and sugars, one of the whole concepts of canning. And especially in a lot of foods, salts and sugars are added. Things like pork. My grandfather would always talk about how they would kill a hog. They just add a crap ton of salt to it, and they put it in a little, it's like a little shed that's all enclosed. I don't know. Glad I wasn't around. And I thought, he's so funny though. He would always leave things sitting out on the stove, and man, I would just be like, "You're gonna eat that tomorrow." It's not even been in the fridge. They put their ham out on the porch.
But they had a great immune system.
Well, yeah. And I would say when I was a kid, because I lived with my grandparents for a while when I was a kid, I'd say I have it pretty good. I probably withstand quite a few things. My mother, man, she kills me too. I have to. She's one of those people I'm like, now let me cook and let me do everything, and you just sit over there. I remember when my husband, we went to, when my grandfather was still living in his house down there, he went and visited him, and he was like, what are they going to do with that piece of ham sitting out on the stove? Like they're going to eat it is what they're going to do, but it's just going to sit out for a while. He was like, oh my God. I'm like, we're not going to eat it. Just to make that clear, but they will.
No.
But I think it goes back to that whole, he's so used to those animals, they were cured, you know, they had so much salt added to them that I guess he just figures nothing's good. As far as some of these chemical controls, chemotherapeutic agents used to treat disease, I'm not going to ask you that definition. I know you guys have been through some of this terminology, germicides and germostats. And again, you don't have to know how many germicides there are and how many manufacturers sell them. I don't care about that stuff. That's good Jeopardy info, but not quite as, I guess, good of information for you guys here. The selection, now that particular bullet point is very important because as you're trying to figure out what you're going to use, you have to select the product that you're going to use based on minimizing the amount of damage to the tissue or the object that you are going to target. You also got to consider the microorganism itself. Now, one of the things, and I wanted to, I don't think we'll do this term. One of the things that you can do with these different disinfectants and antiseptics, they call this the paper disc method, and it's the same way for the antibiotic test. The paper disc method is just a very generic term. But what they do is they'll put the antiseptic disinfectant onto like a little disc. And I make them with like little filters, and I'll soak them in something. You take an organism, and let's say it's a TSA plate. You don't do a 3-streak. You just streak the whole plate and cover it entirely with the organism. And you put these little discs on there, and then you incubate. Now, sometimes they grow around the disc and could care less about what product was in that disc. And then sometimes you'll observe something called a zone of inhibition, where they will not get very close to the disc, and that means that it was somewhat effective. Now, you can see larger zones. Does everybody see a zone of inhibition in these? These are different organisms. That Pseudomonas is resistant to about everything, so they're trying to show you that grew around most of those discs. But the zone of inhibition, where the organism won't get close to the disc, can vary in size. So sometimes there's a smaller zone, sometimes there's a larger zone. So if you have the ability to use the larger one, well, you would use the larger one. But for instance, chlorine there with staphylococcus, that wouldn't be something that we could use in our body or on tissue. So it'd be great for cleaning purposes, but as far as antiseptic purposes, wouldn't be useful. So the only thing I want you to really get out of this is what zone of inhibition means. And the paper disc method is a method for evaluating those antiseptics and disinfectants. When we used to have a lot of extra time, I'd put things like Lysol and a variety of different common cleaning products, or like Listerine, different things that you commonly use on these discs, and we'd test them. Now, the antibiotic susceptibility test looks the same way. You set it up the same way. But now, different companies put different amounts of antibiotics in the disc. So they make these charts that correspond to a certain amount of antibiotic in the disc. You set it up the same way. You place the organism, and we're going to actually do this one. But you place the organism on the plate, cover it, put the discs on, you incubate, and the zone of inhibition, again, is where the organism will not grow around the disc. So even though this, it seems kind of weird as far as this is susceptible and this is resistant. So the organism, if it grows around the disc, it would be resistant to that antibiotic because it could care less that it's there. So you got to think of it in those kind of terms. If there is a zone of inhibition, it will not get close to it. So that means the organism is susceptible to that type of antibiotic. So it's sensitive. You would want to use that.
So this is the behind the scenes that report we get when somebody's infection. This all
That's
these
right.
medications of what's most effective and what's not effective.
That's right. So they've done this type of plate. They've measured these zones. And then they'll put them into a computer a lot of times with these lab sheets, and it'll print out whether they're sensitive, intermediate, or resistant.
So like that one over there by the thumb,
Mm-hmm.
where it's the biggest, that would be like your drug of choice.
Right.
Most likely, but now there's different antibiotics. These discs require different zones of inhibition. Most likely that one is, say, a broad spectrum. So if you can use, and not every physician uses this philosophy, so I can't really speak for this is from a microbiologist standpoint, but if you had the choice to use a narrow spectrum as opposed to a broad spectrum, you would want to use that narrow spectrum that it's still sensitive to, because you would save some of that normal flora, therefore decreasing other secondary infections that could occur. Now, a lot of times people will look at, oh yeah, that's really good idea, just give it to them. And it's not that long of a time period, so they're figuring they're not going to do that much damage. So, and it also would depend on if the patient is, say, taken this narrow spectrum so many times, well, we better switch it up and go ahead and do this because the infection keeps coming back. So there is a lot of thinking that goes into that. But preferably, you would want the most effective with the largest zone, the most effective narrow spectrum antibiotic. But if you had to go to the broad, you would. But like I said, that's taking on a microbiology standpoint. Some physicians see that really large zone and do not care and say that's the best, go for it. And give them an antifungal to go along with it, and that's fine. That's good for them. Now, as far as some of these classes of germicides, I'll go through some of these slides, and you just need to highlight on there the things that I ask that you know, because I use them kind of as a description in your test. As far as the phenols and phenolics, a lot of these things do the same thing. But some of the things they do denature proteins. They act on lipids, so they can disrupt that microorganism cytoplasmic membrane. Examples, you can just go to Lysol and hexachlorophene. As far as the alcohols, they do the same thing. They disrupt lipids, so they would target that cytoplasmic membrane. And also they denature proteins. And as far as minimizing damage to the host and so forth, usually 50 to 70% solutions are the most effective with minimal damage. Next one, oxidizing agents. Those that activate protein by oxidizing functional groups. Some examples here under the halogens of oxidizing agents would be iodine, which is an antiseptic, chlorine, which will be the disinfectant, and hydrogen peroxide also falls under oxidizing agents. And typically that is packaged in a very weak solution, so it is a weak antiseptic. And if you guys remember, I don't know if catalase, that enzyme has been brought up before, but catalase is an enzyme that staph produce that break that hydrogen peroxide down into water and oxygen. So sometimes people say it's not as effective. It bubbles when it does that, and everybody's probably seen that hydrogen peroxide bubble. You are oxygenating, so that may be a plus there, but you are breaking down that solution. So now a lot of times you'll find that dentists will say, okay, gargle with hydrogen peroxide. It'll still bubble, and you still got some staphs that'll get in various places, but the streps don't break it down. So it's kind of, maybe you got a little bit of a better shot at reducing some of those organisms as they overgrow. I'm not really so sure the hydrogen peroxide is that great of a product anyway. On to the next group, surfactants. They can also penetrate the cytoplasmic membrane. They can affect both the hydrophilic and hydrophobic portions of that membrane. So that phospholipid bilayer is completely vulnerable. Quaternary ammonium salts is an example, and so you're going to know there. Alkylating agents, those inactivate proteins. They can attach short chains of carbons. They call those alkyl groups, but you can just know short chains of carbons. Formalin, which all the aldehydes fall into this group, but formalin, which is a 37% solution of formaldehyde. Ethylene oxide, which is in this same group, good for gas sterilization. You can up your amount of formaldehyde and it ends up eliminating a lot more organisms. In the weaker solution, molds and stuff will still grow to a degree, but in higher percentages of formaldehyde, find it very hard for anything to grow. Prions, you guys remember prions? Those still don't fall under the being, I guess, inactivated by formaldehyde technically, so everything else is pretty much susceptible to it, but not that. So if you were to have pure formaldehyde, I mean, be in trouble. There was a guy that drank that in med school, and it's the way he killed himself. But his whole inside, my histology teacher, she's one of those that any perfect sample of the inside digestive tract, man, she was on it. But they used the picture of his small intestine, large intestine, things like that in a lot of textbooks because it was perfectly preserved. As it went down, it froze everything in place. So formaldehyde will kill, it's pretty good at eliminating a lot of stuff. That formalin though, just keep in mind, is a vapor solution. That's typically what they use when you dissect. So it's not straight formaldehyde. Now as far as this slide, food preservation, just know these main bullet points: temperature, pH, water, chemicals. There are a lot of preservatives that are used. As far as water, manipulating whether they salt or taking it out and drying, temperatures, that pasteurization. You'll notice I kind of, for the batch method, I just put 63 for 30 minutes and I put 72 for 15 seconds for the flash. Just kind of making it easier. Usually that's what I put on the test to simplify it. pH, there are some things, especially certain Clostridium botulism, for instance. If it's too acidic, it would not grow. So it grows in things more like green beans and so forth, not like tomatoes or something of that nature. All right. Let's go ahead and get out chapter 12.